Good morning students, welcome to the next unit on equations of motion. So in this unit we will be discussing about the following contents. Okay, let me proceed on to the chapter. Now let us first discuss about what is uniform velocity motion. So before that we already know what is velocity. Now what is velocity? Velocity is nothing but displacement divided by time. Okay. Now, if a particle moves equal displacements in equal intervals of time, this is known as uniform velocity motion. So, what do you mean by that? Let us consider, for example, starting from point O. Okay, so let us consider this distance. Here, at time t equal to 0, displacement is 0, and at this point, if you look at it here, if I drop a vertical line here and draw a horizontal, this will coincide at this point. So, which means at 1 second, the displacement is 10 meters. See the distance, it's been measured in terms of meters. So here, it's in distance time graph. So distance traveled is 10 meters. So therefore, if it is moving in a straight line, I can now say that this is 10 meters divided by 1 second, which will be equal to 10 meter per second. So this will be your velocity. Okay, let me call this velocity v1 here. Now let us consider a time t equal to 2 seconds. Again, let me drop a vertical here and drop a horizontal here. Now when I do this, you see that at time t equal to 2 seconds, the distance traveled by the particle is seen to be 20 meters, and thus the velocity now should now be equal to 20 meters divided by 2 seconds, which again comes out to be only 10 meter per second. So thus if you keep on doing it for each and every trial, okay, let us say I do it even for 3 seconds also, I get v3 to be equal to 30 meters divided by 3 seconds. And thus for every value that I do here, you will always get the same value, which is 10 meter per second, which means the velocity is seen to be a constant over here, or it says that a particle moves in equal displacements in equal intervals of time, which means that for every 1 second the displacement is 10 meters. See, between second and the first second it is 1 meter. Between 5th second and the 4th second, let us investigate this also. 5th second and 4th second, let us find what the distance traveled. Between any 2 consecutive seconds also, the distance remains the same. See, the distance here and the time here. For every time interval, I get the same displacement or distance. And thus you see, when a particle moves in this fashion, you can say that the particle is undergoing an uniform velocity motion. Okay, a plot of the velocity versus time will thus give me a straight line like this parallel to the time axis. The reason is because, see, this is at time t equal to 1 second, I get 10 meter per second. Let us say this is 10 meter per second. At t equal to 2 seconds. At t equal to 2 seconds, again the same value. At t equal to 3 seconds, the same value. T equal to 4 seconds, the same value. And thus the same value continues for every value of time. So thus you can observe that the velocity does not change, or velocity remains a constant. Okay, now let us move on to the next one. I hope you have understood about the uniform velocity motion. Now let us look at the distinction between an uniform and a non-uniform motion. Right? We already learned what is uniform motion. Let us look at the second part also. Let us make this car move. Let me click on this video here. Now, as the car moves, now you see, it has traveled a whole distance of 0 to 16 meters. That means the total distance moved was seen to be 16 meters. Okay, and then I will stop the simulation here for some moment. Okay, and then now you see that initially when the car started from point O and reached this point, the distance traveled was 16 meters and the time taken was 8 seconds. 8 seconds. As a result of this, you found out that the velocity of the car was seen to be 16 meters divided by 8 seconds, which is 2 meters per second. Okay, this is what we had found out. Okay, then now let us look at, just a moment. Okay, now you observe that the car has traveled a distance of from 4 to A to a distance of 4 meters. Let me stop it. Okay, and it has taken a time of 2 seconds. So now what I will do is, let me write it down what is the velocity in the region from O to A. So in the region OA, the velocity v1 is seen to be 4 meter divided by 2 seconds, which should be equal to 2 meter per second. Okay, now let us continue with the simulation once again. We click on this. The car again starts to travel, reaches the point B, and now you see it has just reached the point B at a distance of 8 meters over here. 8 meters over here. and this is at 4 meters here. So therefore the displacement here is 8 minus 4, which is 4 meters once again. Let me write down AB here. So therefore here it should be displacement or velocity V2 should be 8 minus 4 divided by time taken is 2, which should be 2 meter per second once again. Now let us write down once again. Let us redo this experiment once again. Let me run the simulation. Now it started from B and reaches the point C at a distance of 12 meters. I am taking equal displacements and finding out what is the time interval. So therefore, in the region from B to C, I observe V3 should be equal to 12 minus 8 divided by 2, which should now be equal to 4 by 2, which is once again 2 meter per second. Oops, okay, which is 2 meter per second. Right. Now let me run from point C to point D, the same simulation. Let me run the car from point C to D. Okay, the car has now begun to move and it reaches the point D at a distance of 16 meters. Okay, so therefore I have written this as CD in the region CD. V4 is equal to 16 minus 12 divided by 2 seconds once again, which would be 4 by 2, which would now again be 2 meter per second. And thus you see in all these intervals I observe that the car has traveled equal distances in equal intervals of time, which illustrates about the uniform motion. Right? Let me, yes. Okay, so this is what you call as uniform velocity motion. I just depicted it here. Okay, so thus the velocity is seen to be a constant. Okay, now let us move on to the next slide. Now, before that, let me keep it over here. Yes, it's the same. Okay, now let us move on to the next slide. Now here you see, I have described about 4 different types of velocities. Let us understand one by one. The instantaneous velocity is the velocity at a given instant. This is the velocity at a given instant of time. What do we mean by that? Which means that, let us say the car starts from here at t equal to 0, whatever is the velocity. Let us say initially we got 2 meter per second. If I calculate what is the velocity here, if this is 2 meter per second, this could be something like 5 meter per second. I'm just giving you some values. This could be 8 meters per second and so on. At every instant you see the car's velocity is now changing. If it changes something like that, then you can say that the instantaneous velocity is changing. Okay, so therefore there is a velocity at a given instant of time. Average velocity. Let us look at the second term. Average velocity is nothing but it's given by the formula the total displacement divided by total time taken. So this will not be equal to, or this may not be equal to the instantaneous velocity. It can vary. So let us say a particle starts from point A here. It goes all the way along to point B. Then again it takes a roundabout turn and comes back to point A. Okay. So in that case you see the total displacement will now be equal to start from point A, go to point B and again back to A, which means this is equal to 0 and the time taken is t. So thus the answer could be 0. Thus average velocity can take a value equal to 0, right? So which means average velocity just summarizes the value. Okay, it only tells us about okay, what is the average value of the velocity during its complete path. When we say I am going from, let us say, from Bangalore to Chennai, which is at a distance of 330 kilometers, okay, and I travel it in 6 hours in my car. Now what I do is, if you ask me what is the average velocity, my average velocity could be around, how much is it? 6 5s are 30, 55 kilometer per hour. This is what is my average velocity. But do you think that I will always be moving at 55 kilometer per hour in a highway? I will never be doing it, right? See, when I just cross my city and I am on the highway, I will always see to it that my speed goes to something like 80 to 110 kilometer per hour. But when do I slow down? I slow down when I reach a city. Okay, as I am reaching a city, definitely there will be lots of traffic jams, lots of vehicles, so I have to slow down. Okay, so therefore I cannot say that my velocity at a particular instant of time was 55, then it raised to 60, then it went to 85, because you are asking me with what velocity did you travel, with what speed did you travel. We can only say the average speed over here. Now let us look at initial velocity. Initial velocity is the velocity at time t equal to 0. What do you mean by that? Which means that when I started my velocity, when I started my car, I also switched on my timer. Okay, I put on my clock and then I say at time t equal to 0, what is my velocity? So this will be the initial velocity. In this situation, you can see the initial velocity, if I started my clock here at t equal to 0, this should have been 2 meter per second. Final velocity. Now in this case what happens is the car started to move and it continued to move until it reached a final point over here. So at this point the velocity was seen to be 8 meters per second. Okay, at the destination, this is my destination. At destination, what is my velocity? That will be your final velocity. So therefore we find out what is the final velocity at destination. Thus sometimes these four can be equal, sometimes it need not be equal. So thus remember, initial velocity is given by the letter U, final velocity is given by the letter V, instantaneous velocity is given by the letter V of t. Okay, we can write like this, or we can also write this as Vt, and average velocity by V average. Okay, so a plot of velocity versus time for a uniform velocity graph looks like this. We have already seen this. Right. Now let us understand by acceleration. So what do we mean by acceleration? Let us look at this figure. You see a roller coaster is now been moving on. Okay, I hope you would have played very much in this. So as it moves upwards over here, it slows down. And then when it comes down, slowly it starts coming down and rapidly it increases its speed. When it is coming down to this path, you see that the velocity is very, very high, right? Do you agree? Okay, and then it's so funny, right? So to move on this, and then as it goes upwards, it again keeps on slowing down, and when it reaches the topmost point, it again slows down and again it continues in the same manner. So now we have come to know that the velocity in these situations are not going to be a constant like the one we have in car. So it is going to change. And therefore we are going to measure this change over a given interval of time. So acceleration is a measure of how the velocity of object changes with time. How does the velocity change with time? This acceleration is a change in velocity divided by time taken, which is generally given by acceleration is equal to change in velocity. What do you mean by change in velocity? Let us say at this point, the velocity is seen to be u. Okay, and when it came here, the velocity is seen to be v. So as a result of this, the change in velocity should now be equal to final velocity minus initial velocity divided by time taken, which should be final velocity is v, initial velocity is u divided by time taken. Okay, this is the fundamental equation to determine the value of the acceleration. So whenever we say acceleration, we can calculate the acceleration at any point. We always have an accelerator in a car, right? So you have a pedal-like structure in the car wherein you press it. Then what happens is the speed of the car increases. What do you mean by that? Which means that you are now going to accelerate the car. You are going to speed up the car. What is the opposite for acceleration? Opposite for acceleration in a car is nothing but you are going to apply brakes. And this in science terms, in physics, we call this as deceleration. Deceleration, or sometimes we remove this a here and we just write this as deceleration. Okay, or sometimes called as negative acceleration. Okay, the reason is because the acceleration becomes negative. When can acceleration become negative? Look at the formula here. See here, when final velocity is lesser than the initial velocity, which means what? So final velocity, let us say, initial velocity is, let us say, 5 meter per second and final velocity is 2 meter per second. Then A becomes negative, right? Which means that you can see the particle is now slowing down or the car is now slowing down, right? So this is what you call as deceleration. Thus acceleration means speeding up, and deceleration means slowing down. I hope you are getting now. Okay, now. So thus acceleration is given by the formula delta V by delta T. I hope you recognize this delta. Delta stands for change. Okay, let us move on to the next one. Now let us look at variable velocity. Shown here is a gaming video here, which says that there are two cars. One car is moving here and the other car, which I am moving on, I see that, okay, so this is moving much faster. Now what can you say about the velocity here? The velocity here, it's my cursor, right, the velocity here, the velocity of my car is now increasing rapidly like anything in the forward direction like this, okay, as compared to this. That means my velocity is now increasing, or my velocity is a variable quantity. The velocity was not variable, then what could have happened is we both, okay, the first car and the second car would have been at the same distance, and I will never win my race over here. Now let us look at this here. Now as you see here, you see the car starts from here. So as it started from here, let me start, okay, the car started from here, it came to a green signal, red signal. When it came to a red signal, it slowed down and again it started moving rapidly, right? So this is what you call it as variable velocity. That means the velocity which is changing with time is what you call it as variable velocity. Do we have acceleration here? Do we have acceleration here? Of course, you do have acceleration, because acceleration is given by v minus u divided by t. When the velocity changes, then definitely v minus u will not be 0, because v and u are not identical, they will be different. And as a result of this, v minus u is definitely not equal to 0, and thus this will be accelerated or decelerated depending upon whether v is larger than u or v is less than u. Let me write it down here. Okay, let us take up one more example. Okay, before that, let us write down here. If v is greater than u, you can say it is acceleration. If v is less than u, then you can say it is deceleration, or we also give it a new term known as retardation. Okay, now what do you mean by v here? V is the final velocity and u is the initial velocity. Now let us take up this case here. Now what do you say about it? There are three planes which are moving across here. The three cars, I suppose. Yeah, there are three cars over here. Which of them is seen to be accelerated and which of them is seen to be decelerated? Can somebody suggest me what is it? Now let me answer it. So you see this red, green and blue. Who moves faster here? Blue comes first over here. So therefore, the blue car is seen to be accelerated. And then, what about the green car? Green car is seen to be very slow here. So therefore, the green car and the red car, both of them are seen to be decelerated, or what you call it as retardation, right? So when an object is slowing down, the direction of the acceleration is negative. As you see here, when the object is slowing down, okay, you see the acceleration is in the opposite direction. When an object is slowing down, the direction of the acceleration is the opposite direction of the object's motion. See, as the particle is sliding down here, the velocity and the acceleration vectors are opposite, and as it is slowing down, you see, velocity becomes smaller and acceleration is in the opposite direction. Did you notice it? Let me run the simulation once again. See, the particle is coming down, velocity and acceleration were in the same direction from here to here, right? Let us rerun it once again. Okay, you see, velocity and acceleration in the same direction. When it is coming like this, you see, the velocity and acceleration were in the opposite direction like this, right? And then, when it undergoes a circle, now you see, when it undergoes a circle here, velocity is like this, acceleration is like this, acceleration is in this direction, velocity was in this direction, right? So thus, the value of velocity, the directions of velocity and acceleration tells me what kind of motion am I describing. Okay, let us move on to the next case. Now let us look at the differences between an uniform and a non-uniform motion. So what did we learn so far? We have learnt about what is a uniform motion, what are the parameters of a uniform motion, and now we are going to learn about non-uniform motion, okay, and how does it differ. Now towards it, let us run this video once again. Let me start it here. The car started at O, reached at point A, which is at a distance of 2 meters, right? Okay. And now you see from point O to A, the distance traveled is 2 meters, time taken is 2 seconds. Let me write in the region OA, the velocity was V1, which was seen to be 2 meters divided by 2 seconds, which is 1 meter per second. Now, let me run the trial once again. Let me make the car move. I'll click on this play button. Now you see the car starts moving from point A to point B and has reached a distance of 8 meters, right? Distance of 8 meters in 2 seconds, which means the region from A to B, over here, A to B, the velocity is seen to be 8 meters minus 2 meters, which is a displacement, which would be 8 minus 2, which is equal to 6, divided by time taken is 2. This should be equal to 3 meter per second, right? We have got for the velocity V2 also in the region A to B. Now let us run the video once again. The car now starts at B and reaches the point C over here, right? And now let me write down for BC. I hope many of you would have guessed by now. In the region B to C, the distance traveled or the velocity V3 will now be equal to 10 minus 8, which is a displacement, 10 minus 8, and the time taken is 2 seconds. 2 seconds, and thus this will now be equal to 2 meter per second. Sorry, this will be now be equal to 2 meter per second. Then we already run from B to C. Let us run from C to D now. Right, let me stop here. So from C to D, as you observe, so the distance traveled is 16 meters here from 10 meters, which means from CD, now it should be V4 should now be 16 minus 10 divided by 2 seconds. Now what do I observe here? This is 6 by 2, which should be 3 meter per second. Let me run this completely. And what does it say? Now what is the total distance traveled here? 16 meters in 8 seconds, right? See, I will count this. See, the total distance traveled from point O to point D is 16 meters. 16 meters. And the total time is 2 plus 2 plus 2 plus 2, which is 8 seconds. 8 seconds, which should now be equal to 2 meter per second. Let me call this by capital V. Now, can you tell me what are these velocities? You see, the velocity V1 is 1 meter per second here. This was 1. And here it was 3 meters per second, which means it was really accelerating. And here you observe, this is 10 minus 8 divided by 2, 2 by 2, sorry, this is 1 meter per second. This is 1 meter per second. And here it was 3 meter per second. 3 meter per second. Now you see here, the velocities are now varying here. So in such cases, we say that this motion is a non-uniform motion, and thus you will be able to find out the acceleration. The acceleration in this interval, and so on. Okay, now let us move on to the next topic.